Alright, so last time we started talking about postulate number 6 in our list of postulates. And this is, oops, sorry, Schrodinger equation. This is the time-dependent Schrodinger equation, which is given by this expression right here. IH bar, partial derivative of psi with respect to time is equal to h hat psi, where h hat right here is what you would call your Hamiltonian operator, right? So we said that we were interested in cases where the Hamiltonian operator itself, or specifically the potential energy part of that Hamiltonian operator, is independent of time. Okay? We said that the Hamiltonian operator, we learned that earlier, that's the operator that corresponds to the energy of the system. So we said that you can show that there are solutions to the time-dependent Schrodinger equation. We did that. We made the assumption that there are solutions, and we found that if, in fact, there are solutions that you can write as a function of coordinates times a function of time, then the function of time has to be at this form, and the function of coordinates must satisfy this eigenvalue equation. Right? So one thing I forgot to mention is, okay, we made the assumption that there are solutions that are of this form. Okay, by making that assumption, we showed that the function of time must be of that form, and the function of coordinates must satisfy this eigenvalue equation here. Okay, since we did not encounter a contradiction on the way to doing this, then we've proven that there are in fact solutions that are of this form, function of coordinates times function of time. So these types of solutions are called stationary states, okay? And this thing right here, this eigenvalue equation right here, is known as the time-independent Schrodinger equation. So this equation h psi equals E psi is called the time-independent Schrodinger equation. So for the most part, for the rest of this course, we'll be more focusing a lot on solving this h psi equals E psi, this time-independent Schrodinger equation, because we already know the part that depends on time. Okay? So E right here is the allowed energies of your system, and h bar, we said, was h over 2 pi. Okay, so we were interested. Why are we interested in stationary state? Because if we leave it alone, then it will have a constant, well-defined energy. Why? We've just shown that h psi is equal to E psi, right? So if h little psi is equal to E psi, then h hat big psi would be what? H hat times little psi times a function of time. But as far as h hat is concerned, since it doesn't affect time, this f right here is just a constant, right? So you can factor that out. So that's going to be f times h hat psi, little psi. So that's just f times E psi, right? Since h hat psi is E psi. And that's just going to be equal to E times psi times f. And so that's just going to be E times big psi. So a stationary state wave function, the overall wave function that depends on coordinates and time, itself is an eigenfunction of the Hamiltonian operator. So if big psi is an eigenfunction of the Hamiltonian operator, then that means that describes a state that has a well-defined energy, and the energy is E, right? E right there. So by solving for stationary states, we can determine what the allowed energies are for the system. And like I said, we're interested in this because we can verify the validity of the theoretical predictions through spectroscopy. Okay? Remember, spectroscopy gives us information about the allowed energies of the system. In addition to spectroscopy, you can also verify this against measurements of the ionization energy. Like if you were to shine a photon on an atom, okay, the energy you need to remove an electron, okay, is called the ionization energy, right? The energy is, h nu is the energy of the photon, right? And the kinetic energy of the electron you can measure, just like in the photoelectric effect. And so the difference between the kinetic energy of the electron and the energy of the photon is just the binding energy. So it's also gives you information about the allowed energies for the electron within the atom or within the molecule. All right. For stationary state, we can prove that the probability density function is independent of time. How do we do that? What's the probability density function? It's psi star psi, right? So what would that be? This is your probability density function. That's psi, little psi times f star times little psi times f. What would that be? This is little psi star f star little psi f. And these are all just multiplications, so I can rearrange. Right? So I can say this is psi star times psi times f star times f. Right? So what is f star? This one is what? F is e to the negative I e t over h bar. So what is f star? Take the complex conjugate, you see an I replaced by negative I. So in this case, you're going to have e to the negative of negative I. So that's plus I e t over h bar. So this is really like e to the x times e to the negative x. What would that be equal to? E to the 0, which is just 1. So this one will just be equal to 1. So what we're saying is big psi star times big psi is just equal to little psi star times little psi. So it's independent of time. Okay? So that's why it's called a stationary state, because the probability density is independent of time. Psi itself does depend on time. Big psi depends on time, this depends on time. But it's equal to this, okay, which is independent of time. It only depends on the coordinates of your particle. All right, so let's look at an example here. Let's say h size of n, so you have a series of solutions, psi 0, psi 1, psi 2, and so on. Let's say that's your eigenbasis for your Hamiltonian operator. Okay, so h hat operating on that gives you n squared beta times psi n. So these are your eigenvalues, right? The constant that you get is your energy. So let's call that E sub n. And so let's say psi, big psi, happens to be little psi 3 times e to the negative I e3 t over h bar. Okay? What would be the allowed energies for the system? What is E0? 0. What is E1? 1 squared beta. So that's going to be beta. What is E2? 2 squared beta. So that's 4 beta. Right? What is E3? 3 squared beta, which is 9 beta, and so on and so forth. So if we were to try to measure the energy of this system, what is the probability that we're going to get 4 beta? You remember from our earlier postulates? What is our psi in general? C0 psi 0 plus C1 psi 1 plus C2 psi 2 plus and so on and so forth, right? So what's the probability that if you measure the energy, you get 4 beta? Then that's just going to be C sub 4. What's 4 beta? For n equals 2, right? For psi 2. So then the probability that you're going to get the eigenvalue of psi 2 would be C2, absolute value of C2 squared, right? What's the absolute value of C2 squared? Okay, here's C0 psi 0, psi 1, psi 2. What's our psi? You're given that psi is C3 is 1 times psi 3, right? So C0 here is, according to this, 0. C1 is 0. C2 is 0. C3 is 1. C4 is 0, and so on. So what is the probability? It's you were given that psi is just equal to psi 3. So the probability of anything besides the energy E3 is 0. Okay? What's the probability that you're going to get 9 beta? Well, 9 beta is the energy of corresponding to psi 3, so the probability of getting 9 beta is 1. Absolute value of C3 squared, so that's just going to be 1 squared. In other words, that's basically what we said. If psi is an eigenfunction of the Hamiltonian operator, it has a well-defined energy. In this case, what's the well-defined energy? 9 beta. Okay? Because we said psi in this case, and this is supposed. This one says suppose, okay, that psi is equal to psi 3. This is psi 3. Okay, true or false? A system in a stationary state has a well-defined energy. That's true. Okay. In fact, H hat psi would be equal to E psi. E is well-defined. Okay. If it's in a stationary state, it is an eigenfunction of the Hamiltonian operator. Show that any linear combination of degenerate stationary states is also a solution to the time-independent Schrodinger equation. What's our time-independent Schrodinger equation? H hat psi equals E psi, right? So let's say our psi, suppose our psi is equal to C psi psi 1. Let's say psi 1, psi 2. Let me write my psi correctly. Psi 1, psi 2, and so on are the stationary states. Okay, so let this be your stationary states. Then C1 psi 1 plus C2 psi 2 and so on would be a linear combination of your stationary states, right? So what are we trying to prove here? Is psi H hat psi equal to E psi if psi is a linear combination of stationary states? Let's see. H hat, let's just do a linear combination of these two, right? So C1 psi 1 plus C2 psi 2 equals, well, Hamiltonian operator is a linear operator. I can distribute, and I can pull out constants, right? So this is going to be C1 H hat psi 1 plus C2 H hat psi 2. Okay? Well, what is H hat psi 1? That's E1 psi 1. And what is H hat psi 2? E2 psi 2. Is that equal to a constant times the original psi? That's my original psi. My original psi is C1 psi 1 plus C2 psi 2. Can I pull out the constant there? What would be my constant? Only if E1 is equal to E2, right? I can't pull out a constant here. That's why we have to have degenerate. So if we say that if E1 is equal to E2, then this is going to be E1 or E2. Then you say your wave function, okay, the state function is an eigenfunction of the Hamiltonian operator. if it's a linear combination of degenerate stationary states. If it's non-degenerate stationary states, you take the linear combination, then you end up with a psi that is not a stationary state. It's a psi that is not an eigenfunction. So that psi, okay, if E1 and E2 right here are not the same, then you cannot write this as a function of coordinates times a function of time, the overall psi. So we say in this particular case, if E1 is not equal to E2, then your psi is not an eigenfunction of the Hamiltonian operator. You cannot write it as a function of coordinates times a function of time. But this linear combination is still a solution of the time-dependent Schrodinger equation. We're looking here at the time-independent. Okay? And this is our next proof. Thing to prove here. Any linear combination of stationary states, whether they are degenerate or not, okay, is also a solution to the time-dependent Schrodinger equation. So what was our time-dependent Schrodinger equation? IH bar, partial derivative of psi with respect to time, is equal to H hat psi. Right? So this is provided your H Hamiltonian doesn't depend on time, right? So let's do this. IH bar, derivative with respect to time. Let's just do a linear combination of two. So C1 psi 1 plus C2 psi 2. What do we get? IH bar C1 derivative of psi 1 with respect to time, right? That one, and then that one, plus C2 derivative of psi 2 with respect to time, okay? And I'm going to go ahead and multiply the constant there. So this is going to be C1 IH bar derivative of psi 1 with respect to time plus C2 IH bar derivative of psi 2 with respect to time, right? But what is this? C1, this is just H hat psi 1, right? Plus C2 H hat psi 2. Okay? Since the Hamiltonian operator is a linear operator, I can move back my constants in. So I can say this is H hat C1 big psi 1 plus H hat big C2 C2 times big psi 2. And since it's a linear operator, it's the same thing as H hat of C1 psi 1 plus C2 psi 2. Okay? Which is the same thing as H hat psi. And so what we've shown is this thing on the left, IH hat d psi dt is equal to H psi. So what we have shown is IH bar derivative of psi with respect to time is equal to. So any linear combination, they don't need to be degenerate. They will still be a solution to the time-dependent Schrodinger equation. It just so happens that if that linear combination involves non-degenerate states, non-degenerate stationary states, then it will not have a well-defined energy. Okay? If you make a measurement, there's a probability you might get the energy corresponding to psi 1, or there's a finite probability that you might get the energy corresponding to psi 2, and so on. Okay? So let's say H hat psi sub m, look, this is little psi, right? It's m squared b times little psi, where m is 0, plus or minus 1, plus or minus 2, and so on. What if we took the linear combination of psi 3 and psi negative 3? would that still be a solution to the time-independent Schrodinger equation? You're supposed to show that it is, so why should it still be a solution to the time-independent Schrodinger equation? What is E3? That's 3 squared b, which is 9b, right? What is E for negative sine negative 3? It's still negative 3 squared b, so that's 9b. So sine 3 and sine negative 3 are degenerate states. So a linear combination of degenerate states will still be a stationary. Degenerate stationary states, a linear combination of degenerate stationary states is also a stationary state. So let's make this your homework. Okay. So prove that it is a solution to the time-dependent and the time-independent Schrodinger equation. This specific case. Okay.
Don't change it yet, please.
Huh?
Don't change it yet, please. I just want to pick up the last one.
I'm sorry.
I just want to write that right quick.
Okay. Oh, that's just linear combination. So you have C1 psi 3. So that's C3 psi 3 plus C sub negative 3 psi sub negative 3. Those are just your coefficients. So your coefficient here is 2. Your coefficient here is 1. So in fact, that's not going to be normalized, right? What should be the normalized coefficients? 2 squared plus 1 squared is 5, so it should really be 2 over square root of 5 and 1 over square root of 5. Okay, so there should be a normalization constant there. But it doesn't matter if you put that extra constant there in terms of the proof, okay? Because it could be any linear combination. It just so happens that in this case your linear combination is not going to be normalized. Okay, so homework. And this is more of the same, except that in this case, okay, it is a linear combination of non-degenerate states, right? What is E3? 9b. What is E4? 16b. So the linear combinations, this is C3 psi 3 plus C4 psi 4, right? This linear combination is a linear combination of non-degenerate states. Therefore, it will not be a solution to the time-independent Schrodinger equation, but it will still be a solution to the time-dependent Schrodinger equation. Okay? Comment about what we said about if its system is in a stationary state, it will have a well-defined energy. And remember, we said if you leave it alone, but it will just have that energy forever, right? Well, in reality, okay, the lowest possible energy, we call that the ground state. In reality, when you have what are known as excited states are those energy levels that are higher than the lowest possible. They do have finite lifetimes, okay? So even if you if you have, for example, an excited, in fact, that's how you produce emission spectra, right? So you make atoms and molecules in the excited state. They do have finite lifetime. They eventually decay, we say decay back to the ground state in the process, emit light. So that emission of light by an excited state, okay, apparently all just by itself is called spontaneous emission. So why do these excited states have finite lifetime? The reason for that is systems are hardly ever left alone, okay? And so you say your particles, charged particles would interact with the electromagnetic field, and so to really explain a spontaneous emission, you need to have you need to use what's called quantum field theory, which is a little bit beyond this course, okay? A field known as quantum electrodynamics, in order to be able to explain why spontaneous emission does occur. Okay, so the important thing to realize is quantum fluctuations in energy do occur. There is an uncertainty principle associated with energy and lifetime. So Uncertainty in energy times lifetime is approximately at least h bar over 2. Okay? So this is another uncertainty relationship that you need to be aware of. Okay? So that is the last postulate that we're going to cover so far. Sometime later this semester, we're going to add another postulate that has to do with spin. But for the next part of the course after this, we're going to be applying the postulates of quantum mechanics to simple systems. We're going to start with the simplest possible system, the free particle. And then we're going to look at the particle in a box, confined to one dimension. And then we're going to have a particle confined to a two-dimensional box. And then we're going to look at the particle confined to a three-dimensional box. And then we're going to look at particle confined to a ring, particle confined to a sphere, okay? Particle that's governed by a harmonic potential, which is called a harmonic oscillator. It swings back and forth. So, and then we're going to go into atoms. We're going to start with atoms that have only one electron. And then we're going to look at atoms that have more than one electron. And then we're going to look at molecules. Okay, so simple systems, that would be your next test. And then, so your first test ends with this topic. Okay, second test would cover atoms, simple systems. The third test would cover atoms and molecules. All right, so that's that for postulates for now. Let's just let me just give you a preview of an illustration of these wave functions using Mathcad, so you can visualize what's going on with psi, stationary, say psi, and okay, let's see, for what we would call the particle in the box. So sometime later this semester we're going to talk about the particle in the box. So let's imagine you have one particle, let's just say an electron. We're going to confine it to a box of length equal to 1 nanometer. Okay? If we solve the Schrodinger equation for that particle, you'll find, okay, that the wave functions, the eigenfunctions of the Hamiltonian operator would be of the form psi, okay, the nth eigenfunction, which will depend on x, is equal to square root of 2 over L times sine. You don't need to know this one at this point. We'll cover it later, but it's just so you can see what those solutions, what the time dependence looks like. Okay, so sine times n times phi times x over L. Okay, oops. And the function of time, what was it? So function of time for the nth eigenfunction is going to be equal to, you remember, e raised to the power negative iet over h bar, right? So I, the way you enter I in Mathcad is you type 1i. Okay, if you just type I, Mathcad doesn't know what that means. So you type 1i, that's the imaginary number, square root of negative 1. So 1i times e. Now E depends on which quantum state you're looking at. So E of n. So we're going to say E is a function of n. Okay. Times T over h bar. So h over 2 pi, right? We can't do h bar on Mathcad, so we have to write h over 2 pi. Okay, and it's complaining it doesn't know what h is. So let's define h up here. 6.626 times 10 to negative 34 joules seconds. Okay. It doesn't know what time is. Oh, this is a function of time. Okay. And it doesn't know what E is. So let's define the energy. It turns out in this case, the energy for the nth state, okay, if you solve the Schrodinger equation, you'll find that it's equal to n squared times h squared. Oops. H squared over 8 times the mass of the particle times L squared. Okay, so when we get to the particle in a box problem, we're going to see all of these. Now, it doesn't know what the mass is. You have to tell it what the mass is. What's the mass of an electron? 9.11 times 10 to the negative 31 kilogram. Okay, and L, let's just tell it what L is, because it's assuming what L is. L is a predefined variable, so I need to override that. L is 1 nanometer. Okay, and it doesn't know what a nanometer is, so I'll have to tell it what a nanometer is. A nanometer is 10 to the negative 9 meters. Okay, so that's what solutions are for the particle in the box. So if I were to plot from x equals 0 times L all the way to L, so I'm going to put 100 points in my graph. So 0.01, that's 1% of L would be the next point. Okay, and then semicolon allows me to specify the endpoint next. So I'm going to plot from x equals 0 to L. Okay, insert graph xy plot. What am I going to plot here? Versus x, and I'm going to do it in terms of L. And so I'm going to plot here psi of nx. It doesn't know what n is, so I have to tell it what n is. If n is 1, that's what it looks like. If n is 2, that's what it looks like. If n is 3, that's what it looks like. Okay, if n is 4, that's what it looks like. So those are your the time the part that's not dependent on time. Now, what's the overall wave function though? It's little psi times big times f, right? The overall psi. So let's define overall psi. So capital Y, control G makes it uppercase psi. Psi, the Greek letter, is Greek letter for Y. Okay. So this would be for the nth quantum state. This will be dependent on x and time, right? So this is equal to the part that depends on x, which is y, control G, and x, little psi. The part that depends on coordinates times the part that depends on time is f, right? F and comma t. So let me plot that one instead. Big psi for n equals 4. I have to specify x and time. Okay. What happened here?
The bottom is right.
Yeah. Okay, now I have to put the units here. My units would be nanometer to the negative half. Let me just redo this one. Okay, where did we miss? Big psi. Let's plot this from 0 to 1. And let's get a plot from I did define L to be 1 nanometer. And X, I define it to be 0 times L, 0.01 times L. Let me pause this video for now. Okay, I just realized that it's not really complaining about X over L. It can't calculate this because it doesn't know what T is. Okay, so I have to tell it what T is. So I'm just going to say T equals 0 for now. Because I'm going to do an animation. Okay, I'm going to type T equals frame times, let's just do T equals 0 for now. Okay, there it is. And to be more specific, T equals 0 seconds, right there. So that's the same, basically the same thing. What happens at time 0? Basically, this f of t is what? E to the 0 is just 1, right? Yeah, I did start capturing the video again. So when time is 0, your big side is just equal to your little side, basically, right? So let's say for 1, let's go back right there. For 2, for 3, 4. Okay. Notice that what's the peak and bottom of your function? Your sine function goes from 0 to -1 to +1, right? So your minimum value is square root of 2 over L. Your positive value is square root of 2 over L. So this one right here is square root of 2 over 1, which is 1.4, right? And this one, the minimum is -1.4. This is if you have the right units, okay? If you don't put that unit right there, you're going to see different numbers here. So make sure you specify the unit you're plotting. Now, I'm going to make an animation of this. If you recall, e to the I, okay, if you have e to the I x, that's equal to what? Let's just call it IKT. Let's call this e to the negative I omega t. Okay, so what's our omega here? E of n over h bar, right? Now, anytime you have something like this, if you remember your Euler formula, this is cosine omega t plus minus I sine omega t, right? So this is going to be a sinusoidal function, except that it has a real and imaginary component. So if you were to look at what happens here, if I were to advance this time right here, let's say I make that 1 second, it can't show it on the graph because you have a complex number. So psi will not show up on the graph because it's a complex number. But what would happen if I were to take the square of this? Absolute value. So I'm going to pick up the calculator toolbar right there. That's absolute value. And then raise to the power 2. And you can see that's just the square of the function. Okay? If you just take the absolute value, that will work too. And remember, what's the square root of 2 squared? Remember your peak was a square root of 2 over L, right? So if you square that, you can see the maximum is at 2. What would happen if I just took the absolute value without squaring it? And then it's just that, 2 over L. Okay? So it's 1.4. So that's the square, oops, the wave function. Right? So what would happen now if I were to change my time? And I'm going to say, okay, what's the cycle time for the part that depends on time? Anytime you have a cosine or a sine function, it's useful, it's a function of time, it's useful to write it in the form 2 pi over tau. Okay? Because when your t advances by 2 pi, that completes one cycle. Okay, so you just need to figure out tau. Tau is the time it takes to complete one cycle. See, when t advances by an amount equal to tau, you see your cosine, your argument there advances by 2 pi, so that completes one cycle. And if you have something like cosine something times x, it's best to write your coefficient there as 2 pi over lambda. Because when x changes by an amount equal to lambda, you know the thing inside is going to change by 2 pi. All right, so I'm going to write it as cosine 2 pi over tau, okay? E to the I 2 pi over tau. So I'm going to say your E of n here is equal over h bar is equal to 2 pi over tau. So what's my tau? Tau is going to be 2 pi h bar over E of n, right? And 2 pi h bar is just h. Remember, h bar is h over 2 pi. So h over E of n. So I'm going to cycle my time from 0 to tau. So I'm going to I'm going to generate an animation of this graph with my time advancing from time 0 to tau. and my tau is h over e of n. Okay? So here's what I'm going to do. I'm going to define tau, cycle for my period, for my cycle, for my function of time. For the nth quantum state, it's going to be equal to h over e of n. All right? So I'm going to let this cycle through. So I'm going to define my time instead using a frame variable. Frame times 0.02, 0.01 times tau of n. Okay, since I'm going to plot psi 4, so I'm going to say tau of 4. Okay, tau 4, period for n equals 4 is, that's not 0 seconds. It should, let's set our zero tolerance to a smaller number. So that's going to be 10 to the negative 16 seconds. Okay, that's 0.6 femtoseconds. So I'm going to advance my time from 0 all the way to tau for this one. Okay, so let's see what happens here. In addition to this, I am going to plot the real part of psi, okay, for xt. And what's the unit for psi itself? Close parenthesis. Nanometer to the negative 1/2, right? And I'm going to plot the imaginary part of psi for xt. And my unit is nanometer to the negative 1/2. And there it is. Notice the red curve is psi squared, right? And the blue curve, this is the real part of psi. Okay? And the green curve is the imaginary part of psi. Okay? At time 0, what do we notice at time 0? At time 0, this part is 0, right? So everything is real. Well, as time advances, you're going to see your imaginary and your real parts are going to change. Okay, so now I'm going to put here, I'm going to put a little space here, and say t equals, I'll put this in terms of tau, okay, tau of 4. Okay, so I'm going to animate this, view, animate. I'm going to do 100 frames. So since I'm going to step it, each frame will step it 1% of a period. 100 frames will give me one entire period. Okay, and then I'm going to select this section to animate, hit animate. Okay, and there it is. So look at what happens to the real part, which is the blue curve. Okay, look at the blue curve. It's changing. The value at any given point is oscillating in time. Okay, look at the green curve. That's the imaginary part. It's also changing. Okay, it's going through cycles. But look at what happens to psi squared, the red curve. The probability density function is not changing. Okay, so your real part and your imaginary parts are changing, but your overall probability density function, the square of your wave function, is not changing. That's why we call it a stationary state. Okay? So let's try one more thing. And this time we're going to plot psi. We're going to say, let's say psi, big psi, happens to be for a particular state. So let's say an actual psi. Okay, I'm just gonna say A, so I don't have to type the whole word. As a function of x and time. Let's say it's equal to a linear combination of psi 1 and psi 2 and psi 3. Okay, so let's say it's 1 over square root of 5 times psi 2. So it's going to be y, control G, psi of 2xt, right? Minus 2 over square root of 5 times psi 3. So y, control G, 3xt. Okay, what will that look like? Insert graph, xy plot. Okay, so I'm going to plot versus x over L. And I'm going to plot psi, this is the actual psi of A as a function of x and time. And that's what that plot looks like. Okay, at time 0. And so I'm going to advance my time. I'm just going to go again. Same thing, frame times 0.01 times. I'm just going to use the period for tau of 4, okay, for n equals 4. And I'm going to say t equals something times tau of 4. Okay. What's going to happen to my psi if I change my, okay, I'm going to put this in terms of the right unit. So what's the unit for psi? Nanometer to the negative 1/2. Right? And so I'm going to set my axes to go from, let's make this negative 3 to positive 3. So I'm going to do that for my psi. So I'm going to square that. So absolute value square. Okay, so that's my probability density function. Let's make this 5, negative 5. Okay? And so what do I need to do here? I want to show you the real part of psi, the actual psi as a function of x and time, right? And my unit for that is nanometer to the negative 1/2. And that's the real part, comma. And the imaginary part would be capital Y, control G, dot A, xt, over nanometer raised to the negative 1/2. And there's your imaginary part. When time is 0, okay, then you don't have any imaginary part.
What is the difference between RE and MI?
Yes, those are predefined functions in Mathcad. RE is the real part of a complex number, and IM is the imaginary part of a complex number. So now let's do an animation. View animate. I'm going to do 100 frames. And let's see what happens. Let's make that 200 frames. Yes, so we have a little bit more. All right. So let's look at the blue curve. That's the real part. I'm going to play it. You can see the real part is changing. The imaginary part is changing. But look at the red curve. The red curve is a square of psi. It is changing. This is not a stationary state. It's a linear combination of non-degenerate stationary states. It's a solution to your time-dependent Schrodinger equation, but it's not a stationary state. It's not a solution to the time-independent Schrodinger equation. Okay? So, and you can one thing you could do is maybe calculate if you have a lot of these, it's possible for those waves to add up so that you have a very steep packet, you localize your particle into like a little packet here, so you have a higher probability of finding the particle in one particular region. And so that would be a way like you can track sort of the movement of the particle where there's a high amplitude of psi, there's a high value for psi squared. Okay? So I think that's all I got for this one.